Hopefully we are live and you're joining us for the C2 live stream. We'll just get confirmation before I carry on that we are actually live streaming. Looks like I'm getting the thumbs up, we should be good to go. So this is all going to be covering what we need to for the C2 exam and making sure you have a cracking exam tomorrow. If you have any questions, just like normal, we've got the contact science@folkestoneacademy.com email address that you can email your questions to. If they're quick questions, we will answer them over email, either Miss Walker or Mr. Pritchard. And if they're longer questions or any good questions come in, we might do them on the board up here, and we'll see what we can do there. Hopefully, we'll tune into this one and we can have that sort of live interaction, but it will be posted afterwards, so you will be able to catch up on it on the YouTube channel afterwards. We will be posting the video there straight afterwards. The slides, as always, are available on our Academy Science Revision website and should be in the description as well, a link to them, so you can get them if you can't see them up here. We sorted out a few issues with the board though. It should be nice and big for you today, rather than, I know the biology it was quite shrunk down, so hopefully that's a bit clearer. Also the sun won't be pouring in through the window because it's a cloudy day, which means you won't get all the glare on the screen and you hopefully be able to see what I'm doing here. As always, though, you'll be able to hear my voice, so I'll be taking you through all the bits that we need to know, including looking at some of the stuff I covered in C1 just at the start, because some of that can come up, but I'm not going to be going into any detail on that really. That's stuff that they assume, as I said, in the biology is prerequisite knowledge, stuff you've already covered, so you already have that information, and little bits can come up about it, so it's worth just going over that briefly, but really concentrating on this stuff we're going to do tonight. As always, I'm going to start my timer, so I know we've got an hour and a half to go through it, and we should cover everything nicely within that time. If we have some time at the end, I might look at some sort of questions, look at some of the things that may come up from C1, things like that. Anyway, without further ado, going into it. So as I said, this is actually C1, this topic, atoms and atomic structure, but it's worth going over because it's the fundamentals of chemistry and it can come up. Similar to what I said in the biology in terms of cells, cells can be covered at any level. This is atoms, and you need to be able to recognise them and talk about them, recognise the subatomic particles. So just ever so briefly, thought I'd cover it before we moved on. Anyway, our structure of the atom, you should remember, it's got a nucleus in the centre where you find the protons and the neutrons, and whizzing around the outside in orbitals or shells, you've got the electrons. You need to know the charges and masses of each of those subatomic particles. As I say, it's mainly C1 topics, but they can ask you things. You still are expected to use the periodic table in C2, so you can do little bits about that, so it's worth having the background information. Protons, anyway, protons found in the nucleus have a mass of 1 and a charge of positive 1. We can remember it's positive because it's a proton. The mass is 1, it's the only part of, or one of the only parts of the atom that make up its actual mass. The other bit being the neutron, which is also found in the nucleus, this time with a mass of 1 but a charge of 0. It is neutral, it has no charge, the neutron. Then, last of all, we've got the electron. The electron is found in shells or energy levels, if you remember that 288 rule for filling up the electronic configuration, which again, as I say, is a C1 concept, but it's worth knowing or having in the back of your mind. Electrons have a mass of almost 0. You can't actually say it is exactly 0 because it's not, slightly higher, so almost 0 is the answer you need to give. And their charge is -1, so charge on electron is -1. All atoms themselves, if they're in there just atom form or elements, they are neutral because they have the same number of protons and electrons, all protons being +1, all electrons being -1, so they cancel each other out. If you had 6 protons, that would be +6, and 6 electrons, 6 minus, it would equal 0 overall, so no charge on the overall atom. Okay. So a bit of background, as I say, this is mainly C1, I'm just covering the basics, but the fundamental ideas are there, so they're worth having in our head. Moving on to the C2 topics, okay? Rates. Rates is an important topic. It's one that students tend to do well in, so hopefully if we get questions on it, we can get lots of marks for them. The rate is essentially the speed at which a reaction takes place, or how fast the reaction takes place. or how fast the reactants are converted into products, or how quickly the reactants are converted into the products. So that's the basic overview. We can calculate it using a simple formula. There are two separate ways we can do that. The rate of reaction in two ways. You can do it the amount of product formed if you could measure that, divided by the time taken. And the time should be measured generally in seconds, but you can get some data that's given to you. Different things, just use whatever's given to you in that. So the amount of product formed divided by time could be one way of calculating the rate. Another way, just as good, depends what you're given, is rate is equal to the amount of reactants used. And again, that's just divided by time. Okay, so two ways of calculating rate, essentially the same, just the amount of product formed or the amount of reactant used divided by time each time. It's worth showing just what I mean by that in case you're unsure, just in case anyone's uncertain at this point. Reactants are what goes into a reaction, so that's what you put in. Now an example could be, I'm just using general things, that could be A plus B. They're the two reactants for a reaction. And then products are what's formed in the reaction. So in this case, A plus B could go to C plus D. And if we could measure the amount of C being formed, we could divide it by time to work out the rate of reaction, or if we could work out the amount of A that's being used up, divided by time, we can work out again the rate of reaction. You need to know several ways of doing it experimentally. They're quite hot on experiments with rates type questions. They usually put it in some sort of example or context. And there are a few ways we could do it. You should have carried out all of these practicals at some point during the 3 years you've been studying science. And the different ways we can measure it and the ones we need to know. We can collect a volume of gas produced. Now, the volume of gas can be collected using, this is called a gas syringe. You might not have seen a gas syringe. A gas syringe is essentially just a normal syringe with a plunger in it, where you push the plunger in to start with. Then you do a reaction inside a conical flask. The reaction produces a gas, if it produces a gas, such as the decomposition of calcium carbonate with an acid, so adding an acid to a carbonate produces CO2 gas, or the reaction of a metal with an acid produces hydrogen gas, and that gas can be collected as it travels up this tube and fills up the gas syringe. That pushes the plunger out, and there's little measurements on the plunger, on the syringe. As the plunger passes, you can record the amount of gas produced and you would do it in a time, let's say 10 seconds. So every 10 seconds I'd read off the gas syringe, 5 centimetres cubed of gas, next 10 seconds 10, next 10 seconds 15, and so on and so forth as the reaction carries on. So volume of gas collected is a way of measuring the amount. That would essentially be the amount of product formed, and then we're measuring it over time or during a time. So that's one way we need to know. We could do, again, if a gas is formed in the reaction, the loss of mass, because as we know as good chemists that mass is always conserved within a reaction, meaning if you weighed all of the reactants and all of the products, the masses would be the same in each case. A plus B, if you weighed them, would equal C plus D. But in reality, when we're doing the experiment, we might not see that. And the reason being is D might be a gas. And if we did it on a balance like this, we put A, this piece of magnesium ribbon, into B, which was hydrochloric acid, inside a conical flask, magnesium chloride would be formed, which would be dissolved inside the conical flask in the solution, and that would stay within the flask. But also hydrogen gas would be formed, and that would float out through the top of the conical flask, and it would appear to lose mass. So the mass on this balance would actually fall. It would go down based on what you put in, because a gas is escaping. If we could trap that gas and actually measure it, we would find out that the mass has actually stayed the same. So if you put a balloon on top, for example, you could capture it and the mass should be conserved. But in terms of rate, we could watch the mass go down, and hence the amount of gas that was produced would be causing that mass to fall. And again, we could work out the rate by doing it over a set time. So timer, just like I've got as a step off screen one here, I would start this when my reaction starts, when I put the reagents into the conical flask, and then every 10 seconds I would read off the mass as it fell during the experiment. The reason there's a cotton wool bung in the top of this conical flask is so that when the reaction's happening, you will see bubbles. It will be fizzing when the magnesium is reacting with the acid, and we don't want any of the liquid in the flask to escape. We want the gas to escape, because that's what we're measuring, the drop in mass due to the escape of a gas, but we don't want the liquid to actually escape, and because it's fizzing, it could spit a little bit out. So the cotton wool is to prevent the liquid escaping, but allow the gas to escape at the top of the reaction, and therefore the mass to fall. So 2 ways we can do it. One thing I'm going to come back to actually, I talked about this gas syringe. Now, you may not have done it using a gas syringe. You may have done it using an upturned measuring cylinder, which I mean a measuring cylinder that we've turned upside down, and you've placed in a trough of water, which works the same way. The gas, you usually use a delivery tube to put the bubbles of gas underneath the water. They bubble up into a measuring cylinder, and as that fills up with gas, it pushes the water out, and you see the water level drop in the measuring cylinder, and you can monitor the reaction by the amount of gas produced. So another way we've done it, possibly if you haven't used a gas syringe, could be a measuring cylinder turned upside down in a trough of water filled with water itself. The water gets displaced by the gas. Okay? Mr. Pritchard just sneezing there, trying to make it not sound on the camera, but now I've told you anyway, might as well have done it. So, the third way we could follow a reaction is by a change in colour. And a classic reaction for this is sodium thiosulfate with acid, and usually an indicator in there as well, which is like iodine, and it actually goes, well no, this one actually, we don't have to have an iodine indicator, because it actually produces, sulphur is produced in the reaction, solid sulphur with sodium thiosulfate, and the solid sodium actually causes it to go cloudy. Now, in the case of these rates reactions, I'll come back to this, I haven't finished with it, but in the case of these rates reactions, sometimes they'll give you a reaction like this, and they'll tell you to identify how you're going to measure the rate of reaction. And what you need to do is you need to look for these things, which are the things in brackets next to the reactants or the products. Okay? This stands for solid. Now, if a solid is formed as a product, that will cause the solution to go cloudy, and that's why I jumped to that. Because in this one, you're forming solid sulphur in the reaction, causes the solution here to go cloudy, and therefore it actually stops you being able to see this cross, which hopefully you can see underneath the conical flask. So you place the conical flask on top of a cross on a piece of paper, and that cross, if you want to make the experiment fair, needs to be kept consistent in terms of its size and colour as a control variable. You place the conical flask on top of the cross, you start the reaction by adding sodium thiosulfate and hydrochloric acid, and you actually start a stopwatch as soon as you add those two reagents. You wait until that reaction goes cloudy and you cannot see that cross anymore, and you stop the reaction and you take the time. So this time we're not actually measuring a certain gas produced or a weight lost each like 10 seconds or over time. We're actually just waiting for the solution to go cloudy, we can't see the cross anymore, and we stop it, and that's the length of time for the reaction to happen, the reaction to occur. So that would be a method we could use if we produced a solid as a product in the reaction. L stands for liquid. Now, there's not much you could do with a liquid in terms of measuring it. It's quite difficult to measure liquids that are produced. Gases, on the other hand, which is G, you would use the methods that I've described here, so loss in mass or collecting the gas produced. So that's another one you can do. And AQ, if it does come in there, it actually stands for aqueous, which means a solution in water. That's because they can put down these state symbols in reactions and ask you about them. So they're called the state symbols. They show you the states of different things in reactions. The reactants and the products may well have a state symbol by it. So if we're producing a gas, we can use that method or this method. If we're producing a solid in a solution, we're going to be able to use this disappearing cross, is what this is called, method, to monitor the reaction. So that's how we could measure rates, by doing the two equations, the amount of product used divided by time, and then the amount of reactant used up divided by time. We can do it experimentally through these methods. The important thing when doing this is often what you'll get is, and I wouldn't be surprised if they did this in the exam, was give you some data and expect you to plot a graph. And this is something that's really important with these graphs of rate of reaction. From a graph of some data, you can actually calculate the rate from the actual graph. And I wouldn't, as I said, I wouldn't be surprised if one of these type questions happen. If we have our graph, and we look at the graph, often graphs of reactions look the same. They look very similar. They start with a steep line, and then they curve and level out. Okay? Now, at the bottom, you will be plotting time. And over here, you should have units if you're doing it properly. This might be the amount of product formed or the amount of gas formed. If it was the amount of gas produced, it would be in centimetres cubed of gas. As I say, most reactions show this sort of pattern in the data, and that's because there's sort of three stages to it. You could be asked to describe a graph of this. Describe means say what you see. So just describe literally what you see is the pattern. And I always like to split it up into three stages. The first stage is like the initial bit of the reaction, this first bit here, then the middle bit here, and then the final bit here. Sort of A, B, C really. When I'm describing that, initially the reaction proceeds rapidly. The increase in the amount of gas produced over time is very fast. The reaction is rapid. Then the reaction begins to slow down. It doesn't stop, or like the rate will decrease, but the amount of gas is still going up. And then eventually the rate of reaction, the reaction does stop, the rate becomes zero, and no more gas is produced, or the graph levels out. Most reactions show that profile because the reagents are being used up as the reaction proceeds. So as the reaction goes forward, you're getting less and less of the two reagents you've put in and more product, and so eventually you reach this point where you've used up all the reactants and you've produced as much product as you can. Now, as I was saying, from a graph like that you can measure the rate of reaction at any point in time. Why you do that is, if I wanted to measure the rate of reaction, and I'm just putting a random number on my graph, but at 20 seconds, what I would do is I would see where 20 seconds meets my line, there, and you actually have to draw a tangent to the line. The tangent means a straight line which meets the curve on the graph. That tangent tells you the rate of reaction if you can find the gradient of it. Now, gradients, you should have covered it in maths, is the change in y. So the change in y divided by the change in x. So you need to find where these 2 points are on your line, and that change in y, delta is the symbol for a change, and divide it by, and I've got a lot of lines on my graph here now, so hopefully you can still see it clearly, divide it by the change in x. So it's change in y divided by the change in x. Tells you the gradient of the line. And for rates of reaction, to find the rate, you need to draw a tangent at any point. So if I wanted to find the rate at 20 seconds, I would draw the tangent, a straight line, touching the curve, and then I would find the gradient of it by finding the change in y and dividing it by the change in x. If there's a practical questions about rates, they could well ask you to do that, but all rates follow that same pattern. Rapid at first, start to slow down, eventually stop. We can change the rate of reaction by doing several things, and that's what we need to look at next. Now, Rates of reaction, if they ask you a question about it, is going to be about collision theory. Collision theory is fairly simple. It says that for a reaction to occur, particles need to collide with each other. They need to hit each other. Particles are moving around all the time. There are particles in the air around us. Those particles are colliding with each other, and they could, when they collide, actually react with each other. But they need sufficient energy to react. Okay? The particles in the air don't react with each other because they don't have enough energy to react. The minimum amount of energy needed for those particles to react is called the activation energy. Okay? So, collision theory says two things need to happen. Particles need to collide, like these particles in picture A here, but these do not have enough energy, so therefore they just bounce off each other and come apart. If those particles collide with sufficient energy, the activation energy, the minimum amount of energy needed for a reaction to occur, then they will react and they will produce products from that reaction. So collision theory states that particles need to collide with enough energy to react. Now, looking at the factors that affect rate of reaction, all of them generally change one of these two things. They either change the number of collisions in a set period of time, or the frequency of collisions is something you need to talk about, or they change the amount of energy that particles have, or the amount of energy needed for reaction to occur. So whenever you're answering questions about rates of reaction and collision theory, you need to think about two things: frequency of collisions and energy required for a reaction to take place. So the factors affecting rate, looking at each one sort of in turn. Okay? Surface area. Surface area is all to do with breaking a substance up into smaller particles. Something, if you have a big chunk, let's say wood, so if we wanted to start a fire, okay, and we took a big log and we tried to light it with a match, clearly that's not going to work. Okay? The log itself has a large volume, but only a relatively small surface area, because the outside surface is only so much. So it won't light. The reaction's too slow, and the reaction therefore can't proceed. You don't light a fire with a massive log to start with. So what you do is you actually, if you break that log up into tiny pieces of wood, i.e. kindling, you could have the same volume. So that log, if you just chopped it up into, say, matchsticks, and then you tried to light them, they would light quite quickly. By breaking the log up into smaller pieces, you've increased the surface area, because all the surface area is the bits inside, and they're able to react with the particles that are trying to react with them. In the case of burning, that would be oxygen, and the reaction is sped up. So, why is it we need to talk about collisions, collision theory? If you increase the amount of surface area, there is more surface area for collisions to occur, which means there are more frequent collisions. And that's what you need to talk about for surface area. Increase in the surface area increases the surface for collisions to occur, which means more frequent collisions. Doesn't affect energy. Energy stays the same, so they still have to have that activation energy, but there's more frequent collisions, therefore faster reaction. The more frequent the collisions are, the more times they collide, the more likely reaction will occur. This is why in, say, a sawmill, which is where they saw up wood, they have to be very careful, because of all the wood dust that's in the air, that has an incredibly large surface area, and a spark or a flame could ignite the whole thing and cause an explosion, because the surface area of the wood powder coming from the saws is so vast that it's actually an explosive mixture. Concentration or pressure. These are often lumped together because they're sort of the same principle if you understand it. What this means is if we increase the concentration or the pressure, we're increasing the number of particles in the same volume. In terms of concentration, what we're doing is we're adding more particles into the same space. So I always describe it as the classroom. If I've got 20 students in a classroom and they all run around with their eyes shut, they're going to bump into each other every so often. If I double the number of students, I add another 20, so we've got 40 students, and ask them to all run around with their eyes shut, they're going to bump into each other more frequently. In fact, if we double it, they'll bump into each other twice as often. So therefore, if you increase the concentration, you increase the number of particles in the same volume, therefore the collisions are more frequent, or they collide more often. Pressure is ever so slightly different because pressure, you don't change the number of particles, you actually decrease the volume. You make it a smaller space for them to move in. Now, it has the same effect. There's more number of particles in the same relative volume, therefore they collide more often or more frequently, and therefore they react more frequently. Concentration is fairly simple in the fact that if you double the number of particles in the same volume, you double the number of collisions, therefore technically you should double the rate of reaction. There's a required practical about concentration that you need to have an understanding of. Again, you can measure it in two ways. You talk about measuring the rate of reaction either using this gas syringe, which I've talked about, by doing your reaction inside a conical flask, measuring the amount of gas produced, or by a change in colour of a reaction, i.e. the cross disappearing. You could do this experiment with different concentrations of hydrochloric acid and see if the reaction happens faster or slower. If we increase the concentration of hydrochloric acid, we should increase the rate of reaction because we're adding more particles in the same amount of volume and therefore more frequent collision. Then last of all, temperature. Temperature actually does two things. If we increase the temperature, we actually give the particles more kinetic energy. And if the particles have more kinetic energy, they can move around faster. If they move around faster, then quite clearly they're more likely to collide with each other. Again, if we had 20 students in this room, they all closed their eyes, walked around the room, they would collide with each other every so often. If they ran around the room, they would collide with each other more frequently. Similarly, if they sprinted around the room at full speed, they would collide very regularly and therefore have a fast reaction. Now, temperature is an interesting one because it doesn't just increase the number of collisions or the frequency of collisions, it actually gives the particles more energy, so when they do collide, they're more likely to react. More of those particles will have the activation energy, hence they're more likely to react, and there'll be more, and the key term they often look for is more successful collisions. So not only is they collide more frequently, they collide successfully as well, so more likely to react. So temperature has a sort of double effect, if you like. It changes the number of collisions and the amount of energy that particles have when they do collide. The last factor you need to know about is catalysts. The key thing about catalysts, or the definition of a catalyst, is it's something that speeds up the rate of reaction without being changed itself. They are useful in industry, in experiments, when we make things on a large scale, because they lower the amount of energy required for a reaction to take place. So they actually lower the activation energy. This is a reaction profile which you should recognise from C1. This is for an exothermic reaction. I can tell because my reactants are higher than my products, so energy is being given out. But the key thing with a catalyst is this lump you have to get over for the reaction to take place is the activation energy. Now, if the catalyst is added, the hump it has to get over is actually lower. It still starts and ends in the same place, but it doesn't have to get over quite such a high hill for the reaction to occur, because the catalyst has actually lowered the amount of energy required for the reaction to take place. Catalysts don't change the frequency of collisions, they lower the amount of energy needed for the reaction to occur, and that's the reaction profile of it. The way they do that, now they've sort of brought a little bit of this in, it used to be an A-level, is a catalyst provides an alternative pathway for the reaction to take place. So rather than going, if I wanted to get to this side of the board, from this side, if I wanted to cross across the board, I could go all the way around the classroom. I'm sure you know what the classrooms here are like. I have to go all the way around the outside. That takes a lot of energy. If a catalyst was supplied, it might clear this pathway here, so I can go directly across, using far less energy and therefore speeding up the rate at which I can make that change. Okay? So that's how a catalyst, it provides an alternative pathway, it doesn't get changed itself, but it lowers the amount of energy needed for a reaction to occur. A good graph is this one, because it shows the two reactions with and without catalyst. Now, it's good because although I'm talking about catalysts here, you could apply it to any of the factors that affect the rate of reaction. Any of these factors would have the same effect on a graph of the products produced over time. So again, if I've got time in seconds along the bottom, and in this one I've got volume of oxygen produced in this reaction in centimetres cubed. A classic one they use for catalyst is the decomposition of hydrogen peroxide to make water and oxygen, and the oxygen you can collect in a gas syringe or a measuring cylinder and measure over time, and you can actually follow the reaction. So when you haven't got very much catalyst, the reaction proceeds slowly, but it still ends at this point. The volume of oxygen when all the hydrogen peroxide is used up is the same as when you've got more catalyst added. The reaction proceeds quicker. Now the reason I say it's an important thing is because we can tell it's quicker because the line is steeper. I.e. the gradient of this line is greater than the gradient of the blue line. The red line has a higher gradient. Okay, it's a steeper line. They both finish in the same place, so catalysts won't change the amount of product you receive. Similarly, increasing any of these things, surface area, concentration of pressure, temperature, will not change the amount of product you receive via this method, but they will change the speed at which you get them. So you will get to your end product faster with a catalyst than without a catalyst. Okay, so that's the way you can look at a reaction of rates of reaction. Moving on to reversible reactions. Now reversible reactions, you should recognise this symbol here, a little half arrow going forwards, a little half arrow going backwards. Reversible reactions are just reactions which can go forwards and they can go backwards. The reactants can make the products can make the reactants. And generally both reactions will be going on. Now, if you have a reaction like this, you should remember from the last topic, so in C1, the words exo, which means energy is released, and endothermic, which means energy is absorbed. And in this reaction, if the forward reaction of this reversible reaction is endothermic, i.e. energy is absorbed when A and B make C and D, they take energy in, then if the C and D come apart to make A and B, energy is released. And you do need to know that the amount of energy absorbed going this way will be identical to the amount of energy released if we go backwards in that reaction. So if this reaction is endothermic that way, it is exothermic going backwards, and the amount of energies are equivalent. If this absorbed 100 joules of energy, this would release 100 joules of energy going that way. An example that they may talk about, and fairly often they do talk about it in terms of reversible reaction, but we do know in the new GCSEs they look for different ways to ask you the same thing. But I'm still going to tell you about this example because it's a good test for water as well. You use copper sulfate, which has got water with it. It's called hydrated copper sulfate. And it's an endothermic reaction, meaning it takes in energy. So if you heat it up, it absorbs energy, and it actually goes to anhydrous copper sulfate. Anhydrous just means without water, plus water, and the water is released usually as steam. If you take the anhydrous copper sulfate, which is a white colour, and add water to it, it actually goes backwards and gives out energy, so gives out heat, the surroundings get hotter, and it becomes blue hydrated copper sulfate. So you'll see a colour change from white to blue. And that's why it can be a test for water, because adding water to anhydrous copper sulfate actually causes it to turn blue and indicates the presence of water. So that's a reversible reaction they can tell you about. And the amount of energy required to be absorbed to make anhydrous copper sulfate from hydrated copper sulfate is the same as the amount of energy released when anhydrous copper sulfate turns back to hydrated copper sulfate. So that's the reversible reaction, and that's energy changes within it. Okay? Reversible reactions can reach a point which is called equilibrium. Now, equilibrium is in a reversible reaction when the rate of the reaction going forwards is equal to the rate of the reaction going backwards. That's when you say we've reached equilibrium. An example I often talk about would be if you've ever gone in an escalator in the shops, or I quite like the ones you get in the airport, the really long ones that take you to the different terminals. Well, I'm sure you've done this because I've done this, and it can't just be me, but if you decide, right, I'm going to turn around and I'm going to go the wrong way on it, So you're walking and the escalator's moving that way and you're walking against it in the opposite direction. If you are at the point where you are not moving, so you're moving that way at the same speed the escalator's moving that way, you're at equilibrium with it. The reaction is going forwards at the same speed the reaction is going backwards. Okay, so there is an overall no change in the concentrations of reactants and products. Okay, they stay the same at that point because as quickly as A and B are being used up to make C and D are reacting together to make A and B. So as quickly as you're making one, they're going back to the other. So the amounts stay the same at that point, they don't change. But that doesn't mean they'll be equal at that point. It doesn't mean if I measured it, I'll have exactly the same amount of A and B as C and D. That depends on the position of the equilibrium, which is a higher level skill, but I will talk about. But basic equilibrium is in all papers, but the position of the equilibrium is in just the higher paper alone, but I'll come on to that. But essentially, when it's equilibrium, A and B are making C and D as quickly as C and D are making A and B. I know I said lots of letters there, hopefully you followed. But it doesn't mean the amounts of these two will be the same as the amounts of these two. It means the speed of the reactions are the same, but they're not necessarily the same amounts in there. Okay? So the reactants go into products. If there are more reactants than products when we're at equilibrium, so when the rate of forward reaction is equal to the rate of backwards, if there are more reactants than products, we say that equilibrium is shifted to the left side. So you say it's been shifted to the left if, when you've reached equilibrium, there is more reactants than products present, the equilibrium is shifted to the left. Or is positioned on the left, I should say. Shifting will come to. Similarly, if there are more products than reactants in the mixture when you've reached equilibrium, when the rates are the same, then you say the equilibrium is to the right. The position is to the right. Okay? So if we have a conical flask again, we're doing a reaction in it, we add in the reactants, we let them react, but it's a reversible reaction. Eventually they reach equilibrium when the rate of that is the same as the rate of that. And then depending on what you've got more of in there, reactants or products, you would say the equilibrium is either to the left if there's more reactants or to the right if there's more products. Affected equilibrium. Now this is the higher level stuff, so this is a higher level skill to be able to say how you can affect equilibrium. It's based on what's called Le Chatelet's principle. Apologise the colour of that. I know like white on the orange maybe not be showing up too great on the camera, particularly as the sun is starting to come out, just to make things more awkward. But hopefully you've downloaded the slides and you can see them in front of you as well. If not, do it afterwards and watch the video again for the third or fourth time, I'm sure, and you'll get that information again. Anyway, Le Chatelet's principle, I'm probably murdering that name, so I apologise to him, but it basically says that if a system is at equilibrium, a change made to any of the conditions, so remember equilibrium is when the rate of forwards is equal to the rate of backwards reactions. If a system or a reaction is at equilibrium, any changes made to that system, the system will respond by counteracting, i.e. doing the opposite to that change. So it'll try to correct, it's a balance. It's like if I had two equal masses in my hands, if something affected one of them and they started to become unbalanced, I would try to counteract it to shift it back. And similarly, that way, I'd try to shift it back to keep them balanced. So that's what the Chatelet's principle is. If there's a change made to an equilibrium, the equilibrium will counteract it to restore that balance, to ensure that equilibrium is returned, or we return to equilibrium. This can be useful for scientists because they can actually use it to change the conditions of a reaction to improve the amount of product they make. Because generally, scientists want to make product in a reaction. That's the aim of a reaction, to make as much product as they can. And that means a high yield. It's called the yield. The amount of product made is called the yield. The more product you make, the higher the yield of the reaction. Now, if we change the conditions, we can actually cause the equilibrium to shift, and this is where I said shift into the left or shift into the right, to improve the yield of a reaction. One thing we can change is the concentration. Now I'm going to use an example for this. A classic example they used to use all the time is one called the Haber process. It doesn't come up as much, but I'll still put it in there. So we've got nitrogen, which is a gas, reacts with hydrogen, which is also a gas, which is in a reversible reaction with a compound called ammonia, which is a gas. Ammonia is used as a fertiliser, that's why this reaction is quite important. Now I need to balance it, so I need to have 3 hydrogens in there as well. Right, so this is an important reaction that the conditions can be carefully controlled to try and maximise the yield of the product formed. They reach an equilibrium, and in fact naturally the equilibrium is very low. The yield of this is actually not very good at all, somewhere around between, I can't remember the exact figures, 15 to 30% ammonia, so it's not very good. So we can change the conditions and use the Chatelet's principle to try and improve that. One of the things we could do, and they do actually do this by liquefying the ammonia, turn it into a liquid and then running it out, is you can actually remove the ammonia from the reaction. If you remove ammonia from the reaction, the Chatelet's principle says the system will counteract that change to try and restore the equilibrium. What it means is it will actually move the equilibrium to the right to try and produce more ammonia. So if you're removing the ammonia from it, it actually shifts it to try and produce more ammonia as a response. It's like, again, if I had 20 beads in both hands and you started taking them out of one hand, I could just move my hands about, but to make a balance again, I could start putting them into the other hand and try to restore that balance. And that's what the reaction does. It shifts it to the right to restore the balance. That's removing something or changing the concentration of the reagents. Similarly, if I increase the amounts of the reactants in there, again, the reaction will shift to try and remove them from it. It doesn't want more of these. It wants to be equal, wants to be in equilibrium. So it will actually increase the rate at which it's moving to the right, and you'll shift the position of the equilibrium towards the products or towards the right if you add more of this. So removing this or adding more of this will shift the equilibrium to the right. Secondly, changing the temperature. Now, changing the temperature, there's a lot of detail you can go into. It sounds complicated, but essentially what you need to know is if the forward reaction is exothermic, that means it's giving out heat. Decreasing the temperature will shift the equilibrium to the right, to the products, if the forward reaction is exothermic. Okay? So if I go back to my example of an equilibrium, in this case the forward reaction is endothermic, so it gets colder. So if I increase the temperature, it will shift it to the right. Whereas this reaction is exothermic backwards, so if I increase the temperature, it's not going to want to give out more heat, so it will actually end up over here, the equilibrium. The way I try to think about that sort of thing, it's difficult. You can just remember this sentence here. Look to see if it's exothermic. If you decrease the temperature, it'll move to the right. If you increase the temperature, it'll move to the left. The analogy I try to use is if I'm doing exercise, if I'm running about, then I start to get hot. It's an exothermic reaction. I give out heat. Respiration is exothermic. What would I rather be in? Would I rather someone cranked the thermostat right up and made it hot in the room, or turned it right down and made it cold? I'd rather it was cold in the room. So decreasing the temperature would shift me more to more exercise to make me warmer. Okay? That's the sort of way I look at it. It might not work for you, it may. It's up to you whether you use it or not. Changing pressure. Now, changing pressure is an interesting one. Changing pressure is usually used when all the things in the reaction are gases, such as this. Now, what you do for changing pressure is an increase in pressure causes the equilibrium to shift to the smallest number of molecules of gas. So that means in total. So if I look at this reaction here for the Haber process, I've got, scientists are quite lazy, they don't write ones in front of things. If there's no number, then you assume it's 1. So that's 1 molecule of nitrogen reacts with 3 of hydrogen. So in total, on this side, on the left, there are 3 molecules of gas. Whereas on the right-hand side, over here, there is 2 molecules of gas. Okay, so we've got 4 molecules over here and 2 molecules over on the right. If we increase the pressure, the reaction counteracts that change, or the system counteracts that change to try and make itself smaller. Because increasing the pressure means you're crushing it down into a smaller space. It wants to be as small as possible in that space, so it goes to the smallest side, which is over here on the right. So if you increase the pressure of this reaction, you shift it to the right. Similarly, reactions, if you increase the volume, which is decreasing the pressure means you give it more space to be in. It actually counteracts that change and tries to make itself as big as possible. So in this case, if you decrease the pressure, it will shift it to the left, to the largest number of molecules. Okay? So that's a high-level skill using the Chatelet's principle to talk about reactions. But if you remember these key ideas, you can do that, and it's seen as one of the more difficult tasks. So on to hydrocarbons. Hydrocarbons is the next topic after rates, equilibrium, hydrocarbons. There are two types of hydrocarbons you need to know about. First of all, you need to know that hydrocarbons are substances that contain only, and only is key for this, only hydrogen and carbon. Okay, hydrocarbon, the clue's in the name. A substance that contains only hydrogen and carbon. The only is important. If you just say contains hydrogen and carbon, you might get 1 mark if it's out of 2. If it's out of 1, you might not get any. You need to say only hydrogen and carbon. And there are two main types you need to know about. There are alkanes and alkenes. Okay, the ending is the different bit, A-N-E and E-N-E. Alkanes and alkenes. Alkanes you need to recognise as containing only single bonds. Okay, they contain only single bonds, which means they're drawn with just one line between all the atoms in them. They're called saturated, which means they're carrying as much hydrogen as possible. And their general formula, this is quite key, is CnH2n plus 2, which means for every carbon you have twice the number of hydrogens plus another 2. If we take this alkane, which is ethane, right here, we've got 2 carbons, so N is 2, C2. H2N, so 2 times 2 is 4, plus another 2 gives us 6. 1, 2, 3, 4, 5, 6. All alkanes follow that general formula of the number of carbons they've got twice the number of hydrogens, plus another 2. You need to know the first 4 hydrocarbons in the series. They are, well, shown there 3 of them, methane, ethane, and the last one that's missing, methane, ethane, propane, and butane. Okay, you need to be able to do up to 4. After that, they're just the shape. So like a 5 carbon hydrocarbon is called pentane, and it goes on like that. But the first 4 you need to be able to recognise. Now I remember this one, monkeys eat peanut butter. Okay, you can follow that. Monkeys eat peanut butter. Methane, ethane, propane, butane. The names of the first 4 alkanes and alkenes as well. It works for alkenes as well. The first 4 hydrocarbons. Monkeys eat peanut butter. Probably is the next one because it's pentane, but then it goes on to the shapes. Pent is a 5-sided shape, pentagon, so it's pentane. And then hex is a 6-sided shape, hexagon, hexane. So, we know how to name them, we can identify them, you do need to be able to draw them, you can see 3 of them there. Like I say, butane would just be 4 carbons, all joined with single lines, and then hydrogens on them. Carbon can have a maximum of 4 bonds, remember, and hydrogen can only have 1 bond or 1 line coming from it. Alkenes, they're recognised because they contain a double bond. The double bond looks like this equals sign. They've only got 1 double bond in them, so if you've got propene, it just has 1 double bond, and then it has all single bonds to the remainder of them. The number 1 mistake when drawing the structures of alkenes is students will put a hydrogen on here and they might put 3 on this one at the end, just like they were drawing propane, but they'll just stick a double bond in there. That doesn't work because, as I said, carbon can only have 4 bonds. 2 of them are used up by that double bond, so it has 1, 2 more. And this one at the end already has 2 used up here, so it has 2 bonds to hydrogen. That's why this is said to be unsaturated. Unsaturated means it could contain more hydrogen. And unsaturated hydrocarbons, you can test for them using a chemical called bromine water. Bromine water is an orange liquid, which is bromine dissolved in water. If you add it to an alkene, it will go colourless. You cannot say clear, because clear means you can see through it. When it's orange, you can still see through it, just like Ribena is purple, but you can see through it. So you can't say it's gone from orange to clear, you have to say from orange to colourless. It goes from orange to colourless in the presence of an alkene, or an unsaturated hydrocarbon. Whereas with a saturated hydrocarbon, such as an alkane, if you add bromine water to any of these, they will stay orange, they will not change colour. So bromine water is the test for alkenes or alkanes. The general formula for an alkene is actually simpler. It's just CnH2n, which means they've got twice the number of hydrogens as they do carbons. For example, ethane has 2 carbons, so N is 2, and it's got 4 hydrogens. 2 times 2 is 4. Okay. Propene has got 3 carbons, 2 times 3 is 6, 1, 2, 3, 4, 5, 6. And that's how you can check you've drawn it correctly as well. If you remember that general formula, you can check you've drawn the structure correctly when you have to draw them. Hydrocarbons come from fractional distillation of crude oil. Now, fractional distillation, again, is quite a hot topic in terms of being able to describe the process. So you need to be able to talk about how fractional distillation actually works. The steps in fractional distillation are, this is called a fractional distillation column, and you actually run off what's called different fractions of chemicals. Now, fractions are a mixture of chemicals. You don't get pure chemicals from it. They have boiling ranges rather than boiling points. And you need to know some of the properties of these different fractions that come from fractional distillation. So the first step involves crude oil, which is where hydrocarbons come from. All hydrocarbons come from crude oil. Crude oil is the stuff we get from the ground, the black substance that you would think of when you think of like oil from the ground, not vegetable oil. Crude oil is pumped into your fractional distillation column, and it's heated up to about 350 degrees C. You don't need to know the exact temperature, you need to know it's heated up till it's really hot. At that temperature, most of the substances in crude oil evaporate. When they evaporate, they turn to a gas and they rise up the column. So they evaporate and they float up. These little bits of the fractional distillation column are designed to let the gas get up, but no liquid to get back down. Anything that doesn't evaporate at 350 is run off through a pipe in the bottom of the column, and is called residue. And it's used for bitumen, which can be used for the tarmac of roads, and can be used for like flat roofs to make them waterproof, a very thick material. Then as you go up, fractional distillation, it gets cooler. So as it gets cooler, the gases rise up, they cool down. And at the top of the column, it's only about 25 degrees Celsius, whereas at the bottom, where you've heated up, it's about 350. As it cools, they return to their boiling point. So the different fractions go past their boiling point, the different mixtures go below their boiling point, and they condense back into a liquid. Now this is where these bits are important, because they stop the liquid from falling to the bottom or sinking back to the bottom. And then you can run off the different fractions at the different levels and separate them out. Anything that doesn't condense back into a liquid comes out the top as gas, and we can use that as fuel for gas burners and things like that. Those propane tanks and things like that you might get for a barbecue could be from fractional distillation of crude oil. Then some of the other fractions we get gasoline or petrol, which is used for a fuel for a car, naphtha, which is used for making chemicals, kerosene, which is used for aircraft, their fuel, diesel oil, which can also be for fuel for cars, buses, lorries, things like that. Then you get fuel oil, which is used for ships and power stations, so we can burn in power stations to supply electricity. Now, quite key to know is why these fractions have different boiling points and a few of their other properties. Again, it's very small on the board here, but if you could download the slides, I recommend it so you can see this information over here, or look at it on your phone, whatever. But as you go up, as the boiling points get lower, because they condense at a lower boiling point, 25 up here and 350 down here, the molecules get smaller. Now when I say get smaller, I'm talking in terms of, and I'll just go back to it, the hydrocarbon chain or the carbon chain. This is getting longer. We go from methane to ethane to propane to butane to pentane to hexane. We're increasing the number of carbons that are in the hydrocarbon. Now with this, we're talking about a lot more. The things that end up down here in residue usually have around 50 carbons in their chain, whereas the things up here in refinery gas can have up to sort of 4 carbons in their chain, and gasoline has sort of, and petrol has around between 5 to about 8 or 9 carbons in the chain. But essentially, you don't need to remember the exact numbers, you just need to know that the carbon chain gets shorter as you go up. The shorter the carbon chain, the lower the boiling point. And there is a reason for that. I've not got a slide on it, but it's due to, as the chain gets shorter, there are less intermolecular forces between the chains, and they're easier to boil because there's less intermolecular forces to break. Now, again, that's a bit of a higher level knowledge. I haven't put a slide on it, but it's something you might want to have a look at. Other properties of the things that you get, the different fractions you get, include they're very volatile, which means they turn to a gas easily. The shorter molecules are very volatile. These are not very volatile. They don't turn to a gas very easily, which makes them suitable for roads and things like that. You don't want your road evaporating when it's on a hot summer's day. This flows easily. So this means this has got like a high viscosity. They might use that word, which means it flows. It means if you pour it, it would be like water. So if you poured it, it would be very runny. And similarly, this is very viscous. This is very thick. It doesn't flow. So this has a low viscosity, and this has a very high viscosity. It's very thick because it's very sticky. So it'd be like you'd imagine like crude oil to be. So if you poured it, it would run like syrup, like golden syrup. If you've seen that, it would be very thick. The things that are down here. Also, this stuff at the top here, the stuff with the low boiling point, burns really easily. Burns really quickly. Just put a match to it, it will catch fire instantly. It will also burn with a clean flame. You won't see any smoke produced when the flame is burning. Think of our Bunsen burners in the labs. They're methane. They have 1 carbon. They burn very quickly. We just put a match to it, it ignites, and when we turn it onto the blue flame, we don't see any smoke produced. No smoke is given. Whereas if you burn these ones down here, so fuel oil, think about a power station, lots of smoke comes out of the chimney because it doesn't burn as easily. It's also hard to light. You have to heat it up quite hot to actually get it to catch fire. Not like petrol, which will light fairly easily. Okay? So that's the difference between the small molecules and the big molecules, or the big carbon chains down the bottom. So they often talk about, with these things, supply and demand. So the demand for some of these shorter fractions, such as petrol particularly, is quite high. Petrol we use in our cars, we need a lot of petrol. We don't get loads of it from fractional distillation. We get quite a lot of fuel oil and maybe residue. We get the longer hydrocarbons rather than the shorter ones. So there's a process called cracking that we can do. This is considered a long hydrocarbon, even though it's only 1, 2, 3, 4, 5, 6, 7, so heptane would be its name. This is still considered a relatively long hydrocarbon. And we can crack it into smaller hydrocarbons by exposing it to a high temperature. So if we add a catalyst and use a high temperature, a very high temperature, we can actually crack it into smaller hydrocarbons. So in this case, we've cracked it into ethene, and we've cracked it into 1, 2, 3, 4, 5 pentane as well. So we've cracked our molecule, our heptane, 7 carbons, into ethane and pentane. Now what you should notice is the number of carbons here is the same as the number of carbons here, and the number of hydrogens will also be preserved. And they can ask you, when they're asking you a question about cracking, they can give you a reaction for cracking. They can give you something. I'm not going to use heptane, I'll use decane. So C10H22, twice the number of hydrogens plus another 2. If I crack it, so I'll add a catalyst and a high temp, like plus 500 degrees, something like that. I can crack it into smaller pieces. Now in an exam, what they can occasionally do is they'll give you part of the answer and they'll say you've got to work out the missing bit. So let's say, I'm just making this up, it cracks and it breaks it to C6H, let's go for 14. Okay, and it's broken into one other substance. Now they could have more than one other substance. You can crack it into, say, 3 different substances, but I'm only going to do it into one other substance. Now, in the case of this, I need to look and just work out. It's just like a simple maths problem. Just look at the carbons first. I've got 10 carbons over here, and I've got 6 over here. So clearly, if I take 6 away from 10, I've got C4. I've got 4 left over. Then same with the hydrogens. I've got 22 here. I've got 14 over here. If I do H, 8. So the difference is 8. 22 minus 14 is 8. That's my product from cracking. I've identified the missing thing. Now, because it's less than 4, and well, it's less than 5, I should say, you could ask to be asked to name that molecule as well. Now, I remember in my monkeys eat peanut butter, I know butter is the 4th one, so it's going to start with but or bute in terms of this. Now, also, I can tell its name because if I use my general formulas, what's it got? It's got twice the number of hydrogens as it's got carbon. So, in this case, twice the number, not plus another 2, just twice the number, means it must be an alkene. So I've produced butene in this instance, so I've named it as well. The short alkanes, the reason you do cracking is because there's more of a demand for the shorter hydrocarbons, such as the fractions like petrol, but also the short hydrocarbons, such as this pentane, can be used as a fuel because, as I said, it burns very easily, it produces a clean flame, doesn't produce much soot. Soot is carbon from incomplete combustion, which I'll come on to in a bit. And then the alkenes can be used to make polymers. Polymers are plastics, so you can use the short alkenes to make polymers, plastics, and the short alkanes as a fuel for like burning in cars and things like that. Polymerization isn't a big thing in the GCSE anymore, so I'm not going to spend too long on it, but essentially polymers are made from monomers. Monomers are alkenes, and monomers have a double bond in them. Monomer means single unit, like mono means single. So monomers are single units. These can be linked together to make polymers. Poly means lots. These are plastics, essentially. Now, to draw a polymer from a monomer, you essentially just have to draw the monomer out again without this double bond in it and a single line, and put some lines going outside of a bracket to show that this is what we call a repeating unit in a chain. There can be lots of these linked together. Similarly, if you want to draw the monomer from the polymer, if you've got given this, you just take these lines off the outside, get rid of the square brackets, and put a double bond in the centre. Draw it out exactly like it is there. I'm not going to go on too much about it because polymerization is something that's been really stripped back in the new GCSE, but I thought I'd make you aware because some of the products from cracking can be used to make polymers. Right, so that's hydrocarbons covered. So we're moving on to some of the later topics now. Chemical analysis is one of them, and this talks about formulations. What a formulation is, it's a mixture that's been specifically designed to be a useful product, used as something. Examples would be like medicines, like tablets. Tablets only have a small amount of what we call the active ingredient in them. So when you're taking your paracetamol tablet, it's not all paracetamol you're taking. It's a tiny bit of paracetamol, and if you read the label, they'll say like 200 milligrams paracetamol. And then the rest of it, if you actually weighed the tablet, it probably weighs like 500 milligrams or half a gram. And some of it is actually just the stuff they make it up with, which can be various things, starch, carbonates, things like that. So medicines only have a small amount of active ingredient. The thing that has the active effect actually makes you better is a tiny proportion of the formulation that you're actually taking, the tablet that you're taking. So medicine, food products also have a formulation. They're made up often. They have to have a specific amount of different things in them to be correct. Paints, there's only a certain amount of pigment in there. The rest of it's like usually an oil or water mixed in oil, emulsion-based paint. Fertilizers that you might use to grow plants have a certain ratio of different substances in it. And they have to be made up to very specific ratios. So they have to be made up to the exact mix. Particularly important for medicines, Okay, if you have a certain level of active ingredient, of actual drug that you have in a tablet, it has to be exactly that each and every time. And they'll actually do, the drug standards agency would do testing on the different drugs that are produced by different companies to ensure they're putting in exactly the correct amount of ingredients into it that they're actually stating on the back of the packet. If it's out within just a few milligrams or a few tiny little bits, then they can reject it and say no, this is not good enough, it's not a correct formulation, and it's being rejected. Okay, so essentially formulations is just a mixture with a useful material. We also need to know the tests for different gases. Now, some of these tests are really quite simple and some are a little bit more involved. The test, you should have come across these before. Test for carbon dioxide, use a chemical called lime water. Lime water, again, is a clear, colourless solution. And when you put carbon dioxide gas into lime water, it becomes cloudy. It stays white. You can say it goes milky, in fact, but cloud is the word I prefer to use because you can no longer see through it. So the test for carbon dioxide is using lime water and seeing if the mixture goes cloudy. Now with this test for gases topic, actually, it's worth pointing out that there's very unlikely to be a whole question on this. This is more likely to be a part of a question. So a good example would be a rates of reaction question, and during that rates of reaction question, one of the products may be carbon dioxide gas or hydrogen gas or oxygen gas, and they might ask, how would you test to confirm the gas is actually carbon dioxide? In the case of carbon dioxide, you would add it to lime water and see if the substance goes cloudy. Test for chlorine gas, Cl2. Chlorine actually bleaches litmus paper, so you use what's called blue litmus paper, which usually tests for acids by going red, and if you put it into potentially what you might think will be chlorine gas, it will bleach. So first of all it will go red, then it will go white as it bleaches the colour out of it. Chlorine's very good at bleaching things. So test for chlorine is to bleach damp litmus paper. It goes from blue to red to white. The colour gets bleached down. Hydrogen. The hydrogen test is called a squeaky pop test. If you take a gas in a test tube that you believe to be hydrogen, you take a splint that you've lit, that's one of those little bits of wood we use in science, could be a match, and you place it just inside the mouth of the tube. If it is hydrogen gas, it's a little mini explosion, but because it's in a test tube, it usually gives a squeaky pop, hence the name. But that's the test for hydrogen gas, the squeaky pop test, a little mini explosion. Test for oxygen. Oxygen is similar. If you have a tube containing what you believe might be oxygen gas, if you take a splint, but this time you have to blow out the splint and then place it in the tube. If oxygen is present, the splint will reignite. It's called the reignited splint or reignited glowing splint test. So take a splint or a match, blow it out, place it in the tube you think might be oxygen, and does it relight? Yes, it's oxygen gas. Last of all, there is a test for water as well. May not come up. We already looked at anhydrous copper sulfate will turn from white to blue. You can also use a chemical called cobalt chloride paper, which is just paper with blue cobalt chloride on it. If water is present, it actually turns from blue to pink if water is present and you're testing it for cobalt chloride paper. Okay? But these 4 tests for gases are quite crucial to know. Water you can test for the vapour as well using cobalt chloride paper. And then chromatography. Now this slide I know is very busy, so I'm trying to break some of it down for you. The reason it's quite busy is because this is again a required practical. I said changing the concentration and measuring the rate of reaction was a required practical. Chromatography is a required practical as well. So you need to know a method to do it. And I'll quickly run through the method. Essentially you take a piece of usually filter paper, but you can call it chromatography paper, which is a square or rectangle I should say. You draw a pencil line on the filter paper about 1 centimetre from the bottom of the paper. You then use what's called a capillary tube, which is a very thin, small glass tube, to place a dot of an unknown substance, possibly a dye if we're looking at colours, onto your pencil line on the filter paper. So you just touch it with the capillary tube, the dye that you've dipped the capillary tube into the dye, touch it to the paper, the dye runs out and you get a little spot on your filter paper or chromatography paper. You then do the same on that pencil line, but just along from it, not in the same position, with a known dye or colour or substance. So you place a dot, again using the capillary tube, of a known substance on the pencil line next to your unknown substance that you're testing. You then need to add a solvent into a beaker or a chromatography chamber, which is no higher than 1 centimetre from the bottom. The reason being, this is quite crucial for it, you don't want your solvent to be higher than your initial pencil line, because it will cause the chromatography to run all out into the water, into the solvent, and make a mess, and you won't get good results. So your solvent needs to be less than 1 centimetre or below that line you've drawn on the chromatography paper. One thing this just made me think of, why you use pencil as well, is because when that solvent, when the chromatography is actually running, the solvent will run up the filter paper. So once you've added your chromatography paper, filter paper into your beaker, you need to leave it so the solvent is drawn up the paper. Pencil will not run. If you've used pen to draw that line, particularly the handwriting pens we have here, the ink will run along with the solvent and dissolve into the solvent, and it will cause a right mess. So pencil line. You also need to place a lid on top to prevent evaporation, to ensure the solvent moves up the paper and doesn't start to spread out as it evaporates. And once that solvent, so step 4 is allow the solvent time to rise up the paper until nearly at the top of the paper. You can then remove the chromatography or filter paper from the beaker and you have your chromatogram laid out, so removing of it. Afterwards you'll see something like this. Now this is where we've done maybe comparing two substances together and we're looking to see any patterns. There's a few things we can tell from chromatography. The first thing we can tell is whatever we spotted here and here on either side of our chromatography paper, both had 3 substances in them. So we actually separated out the mixtures. The way it separates out mixtures is it relies on the solubility. The more soluble something is, the higher it will rise. The less soluble, the less easily it dissolves, the lower down it stays. Both of these substances have produced 3 spots in their chromatogram. So they had 3 substances in the mixture. So that's the first thing we can tell. They both had 3. One might have had 3, one might have had 2, one might have been a pure substance and only had 1. But that's something we can tell. Now it's a comparative technique, as I said, so we can actually make comparisons. These 2 green spots at the bottom, they are at exactly the same height on the chromatogram, so therefore it is likely they are the same substance. So if we had a known dye and an unknown dye, we could say that they contain some of the same substance in them. Similarly with this second blue spot, they are at the same height. So again, they are the same substance. Whatever that is, it is the same substance. The yellow spots, on the other hand, are not at the same height. So therefore, these are different substances. Now if this was a food colouring maybe, and we knew that this additive, this dye, this food colouring, this was a safe food colouring, and this was an unknown food colouring, we could not be certain that this one was safe. This is the same, this is the same, so that would give us some confidence, but we don't know what this is. This is as yet unidentified. So we could not say that this unknown substance over here is safe. It wouldn't guarantee it was unsafe just because it was different, but we couldn't tell that from just the chromatogram. Okay? If we knew these were all safe, we know we've got 2 of them, but we don't know what this one is. It isn't the same, so we don't know this whole substance, this whole food colouring, this whole dye is safe for people. So it's a comparative technique. You're looking number of spots, and then you're looking the relative heights of the spots. Finally, one thing you can do with chromatography is when you've got your chromatogram, you can take some measurements and you can actually do a calculation. You can calculate what's called the RF. The RF value is the relative height of the dyes compared to the solvent front, which is the total height of the solvent overall. I know the sun's out now, so I hope there's not too much glare on the screen on the feed, because we have got the sun sort of shining through. Hopefully you can still see it, but as I say, you could be able to hear me, and if you download the slides you'll be able to see it, hopefully. Anyway, if we measure the height of this blue spot from the initial line we drew, it might measure out as 4 centimetres. So that blue spot has risen 4 centimetres up the chromatography plane. Our solvent front, that's the height the solvent actually reached. If we measured that using a ruler, that might be 10 centimetres. The solvent has reached 10 centimetres. Then to calculate the RF, all we need to do is the distance moved by the substance, 4, divided by the distance moved by the solvent, 10, to calculate our RF. 0.4 in this case. So if you know the distance moved by the substance, divided by the distance moved by the solvent, that will tell you the RF value. And again, RF values can be used to compare different substances. If they have the same RF value, we can draw some conclusions about possibly being the same substance if they have the same RF value, identical RF value. So that's analysis. That was the analysis topic. Moving into 2 last topics, the atmosphere and then sustainable development. We've got about 20 minutes left, so we'll get through these nicely. First of all, we need to know about gases in the air. That's the air around us. The atmosphere, they sometimes say, but it means the general air around us, the troposphere, the lowest sort of levels. The gases in the atmosphere have changed over time. They've changed quite dramatically. We would not have been able to survive on the early Earth because the gases in the air were not conducive to human life. We would not have been able to survive. The percentage gases in the air as it stands now, you need to know that the majority of it is actually nitrogen, about 78% nitrogen. Nitrogen is fairly unreactive, so we sort of breathe it in, we breathe it out. It doesn't really take much part in many reactions that are going on because it's fairly unreactive. Oxygen, on the other hand, there's 21% of that. Oxygen is generally quite reactive. We need it for respiration inside our bodies, so we need to take oxygen in. And it's used when anything burns, it's reacting with oxygen in the air. If this percentage was much higher, technically, every time you lit a match, you would almost have an uncontrollable fire burning on your hands. It would burn so quickly. The other gases, the majority of it is argon, so like 0.9% argon. There's about 0.04% CO2. Now, we're going to talk about global warming and climate change and how bad CO2 is for that. Technically, there's only a tiny amount of CO2 in the atmosphere as it stands, but it's talking about changes in this. If this rises, even by a small amount, that can have a big effect on climate change and global warming, as we'll look at a bit later. But you need to know approximately the percentage of gases in the air they are today. We can get this information by doing fractional distillation, cooling down essentially air and working out the amounts of these different gases in there. So how have these gases changed over time? Well, they've changed because the early atmosphere, the early Earth, was very volcanic, very active. There was volcanoes, huge volcanoes blasting off all the time, releasing huge amounts of CO2 and also nitrogen into the air. So these massive amounts of CO2 were erupting from volcanoes into the atmosphere, so really high levels of CO2. Then sort of 2 things happened. They reckon that water sort of fell to the surface and became the oceans as it sort of cooled and condensed and precipitated down. They also reckon that water could have been brought by sort of asteroids and meteorites that came into the Earth. So it actually started to form the oceans. We're about 80% covered by sea on the planet. And the oceans actually dissolved some of the CO2 into their substances, so actually into the water. Also, CO2 became locked up in rocks, and eventually, a bit later down the line, it became locked up in fossil fuels when plants and animals started to appear and then die and then become compressed into coal and oil, fossil fuels that we use. But essentially what happened with that CO2 is plants and algae evolved. Now, it probably started in the oceans, like phytoplankton and things like that, and algae appeared, which actually started doing this amazing process called photosynthesis. And it's worth recapping on photosynthesis if you didn't know it. Carbon dioxide plus water produces glucose, which the plants and algae use for food, and oxygen. Okay, so that was photosynthesis. So that started to occur. It actually lowered the levels of carbon dioxide in the atmosphere and had the side effect of actually raising the gas oxygen, which wasn't present early on. So the amount of oxygen started to rise up, which actually led to the evolution of animals and organisms such as that. So these animals evolved and started doing respiration, which again is worth remembering that respiration is the opposite. Glucose plus oxygen goes to carbon dioxide and water. And that backwards process actually produced more CO2. And then the plants could photosynthesize, and it became a balance, and it levelled out around the levels we are now. Nitrogen, as I say, didn't change too much because it was very unreactive, so the levels kind of stayed about the same, fluctuated a bit in terms of the other gases that were there. So that's essentially how it evolved, the atmosphere evolved into what it's like now. 78% nitrogen, 21% oxygen, 1% argon, and a few other gases such as CO2, an important one. So I said the levels of CO2 are important because of a process called climate change. Climate change is the overall change in weather patterns and temperatures across the globe. People talk about global warming, which just means the Earth's average temperature rising, which is obviously an issue, can lead to melting ice caps, rising sea levels, things such as that. Difficulties growing crops in some areas, less land to do that on. It works by the greenhouse effect. You probably can't see all of this picture here, but again, as I say, if you've got the slides, you'll be able to see it. Essentially, the atmosphere of the Earth has a natural greenhouse effect, which causes us to actually stay warm on the planet. We need to keep some of the Earth's, the sun's radiation within our atmosphere to keep a temperate temperature, a nice temperature for us to live and survive on. But we're actually enhancing the greenhouse effect. We're actually causing more radiation from the sun in a variety of wavelengths to be trapped inside the atmosphere and actually become retained as infrared radiation, as heat, and actually causes the global temperature to warm up. Now, greenhouse gases they're usually talking about, CO2, methane are the main sort of ones. And carbon dioxide levels, we're affecting them, we are rising them because of combustion of fossil fuels. I'll look at combustion reactions in a second. And also deforestation, that has a negative impact because plants, trees, they take carbon dioxide in, convert it with water to glucose and oxygen, so they lower the amounts of carbon dioxide in the atmosphere. If we're cutting down large areas of forest, deforestation, then that means they're less able to take in CO2, and again it contributes to the CO2 levels rising. Greenhouse gases lead to the greenhouse effect. The greenhouse effect is nicely described here. I'm not going to go through it all. Have a look at the slides and you can read that for yourself. Also, another greenhouse gas that I mentioned, methane, CH4, is an alkane. We should recognise that because it ends in ane. Methane means it's got one carbon, so CH4. Methane levels are rising because of the increased level of farming. Now that can be animals farming, and some animals such as cows are notorious for producing methane gas, but also farming of like rice in China, rice fields. Rice actually produces methane when it grows, and this actually raises levels of methane in the atmosphere. And methane is actually a horrible greenhouse gas. It actually has a massively worse effect than carbon dioxide on many levels. It's just the levels aren't generally as high, so we don't worry about it as much. But it's still an issue because of human factors, the increased amount of farming. Also, decomposition of waste. The waste that we dump in landfill site slowly breaks down, and that actually can release methane gas. A new sort of thing, and they could talk about it, is where they actually trap that methane that's produced from our waste products and actually use it as a natural gas which can be used to heat homes, and they can burn it to produce electricity. So I said I'll talk about burning fuels. This could come into hydrocarbons, but could also come into changes in the atmosphere, so it's tied into both. Okay? When fuels burn, such as hydrocarbons are fuels, we're talking about hydrocarbons, enough oxygen, if there's enough oxygen around, they will always release carbon dioxide and water, two products that always form. So an example could be if we burn fuels such as ethane. So when ethane burns, it reacts with oxygen. When any fuel burns, it reacts with oxygen, and it produces, it's a hydrocarbon, remember ethane. Most fuels are hydrocarbon, so they only contain two things, carbon and hydrogen. So when carbon reacts with oxygen, you get carbon dioxide. And when hydrogen reacts with oxygen, H2O, water. Okay? Now you could be asked to balance a simple equation for it. I'm not going to go through again because of time, but if you do want to see me tomorrow morning early on, we can maybe talk about it then. But complete combustion, if there's enough oxygen around for it to react fully, it only produces carbon dioxide and water. Okay? And they often will give you half an equation here and expect you to complete the rest. Incomplete combustions, where there's not enough oxygen around. Incomplete combustion, if we burn a fuel, such as a hydrocarbon, with oxygen, it produces carbon monoxide. Now, carbon monoxide is bad because it's toxic or poisonous to us. So incomplete combustion is bad because it produces a toxic gas. They worry about it with boilers that are not working efficiently within your home. If they're not getting enough oxygen in because the intake of gas has become blocked, they can do incomplete combustion and release carbon monoxide. Carbon monoxide is a colourless gas, you can't see it, it doesn't have a smell, but if you breathe in too much of it, it will block your body's ability to get oxygen and will cause you to kill. It's called cause you to die. It's called the silent killer. It still has hydrogen in it, the fuel, so it still produces water as a byproduct, and it can produce carbon. Now, carbon is the soot I was talking about. Soot is produced, and soot is just carbon. That's why it's black, because carbon is black. So soot can be a sign that incomplete combustion has occurred. Other pollutants you need to be aware of are sulfur dioxide. Fuels generally, such as hydrocarbons, have small amounts, tiny amounts of sulfur impurities in them, and when sulfur reacts with oxygen, it produces sulfur dioxide. When sulfur dioxide goes into the atmosphere, it produces sulfuric acid, and that means acid rain. So if you're thinking about sulfur impurities in fuel, think sulfur dioxide, think acid rain. It's a really common linked sort of question they ask you about. You can get nitrogen oxide released as a pollutant. Nitrogen oxide can lead to acid rain as well because it forms nitric acid in clouds, but it can trigger asthma attacks in people who are asthmatic and cause problems there. And particulates, they're tiny solid particles. More often than not, these bits of carbon in the soot I'm talking about, when they get into the atmosphere, they can be absorbed into our lungs and could cause damage and can in some cases lead to cancer. These tiny little solid particles called particulates, little bits of carbon which block up our airways and cause us problems. Other fuels we can use about that are good can be these. Now, I'm not going to read through them all because we are getting close to the end. I've still got a bit to cover, so have a look at that one to look at some alternative fuels. Moving on to the last unit, we need to talk about sustainable development. Sustainable development is all about utilising the Earth's resources, that's what is available to us on the Earth, to sustain human life. Now, it's a lot about talking about renewables and non-renewables. Something that is renewable means we can always get more of it. Whereas something that's non-renewable means we will run out of it eventually. It is a finite resource, whereas a renewable is infinite. Non-renewables are talking about like coal, oil, natural gas. These are non-renewables. Once we've used them up, they'll be gone. We could also then be talking about like crude oil in terms of making plastics, non-renewable. So we will not be able to continue to make plastics if we run out of crude oil, both for fuels and for making more plastics. Could be talking about non-renewables in terms of different metals that are within the Earth's crust that we're mining out to make loads of things made of metal. We are running short of those as well. Renewables are things like wood, for example, is a renewable resource that objects can be made out of, that's great, and also it can be burnt to release energy, which is also good. Even though it does, when it's burnt, release some CO2, but the trees, when they grow, take in CO2 when you're growing them. So thinking about that idea and thinking about how we conserve the Earth's resources, one of the resources we need to think about is water. Now, potable water just means water that is safe to drink. Water in each country is slightly different, but if it's safe for human consumption, then it is called potable water. The way we get it mainly in the UK is we get rainwater fall onto like hills. Well, we have a few mountains around, not that many, not as many as some countries like Canada and places like that, but we have a few. And the rain falls usually up in the hills or on the mountains, and it actually dissolves some of the gases in the air and runs down into the ground. Then that water can soak into the ground and become groundwater, or it can collect in rivers that are flowing down the mountains and the hills, or it can collect in lakes, or we could add into that reservoirs that have been man-made where we collect water that we can use. Generally though, I mean, if it's fresh water, if you're drinking from a river that's free flowing, you can get fresh water or a stream that is pretty much safe to drink as it is. But most of the water that we have coming from our taps has to be treated. And you need to know the main stages in treating water that we have coming from our taps. The three main stages are sedimentation. Sedimentation involves leaving the water in a big tank, and all the sediment, all the particles in it, tiny particles, sink to the bottom. Okay, they sink to the bottom and they can just be left there. At the top, the water, where those particles have been, sedimentation has taken them out of it, can be run off into a separate tank, a separate container. So sedimentation, particles sink to the bottom, the water is run off the top. Then it's passed for a fine filter, so filtration. This filter is usually sand, so they use like sand and they let the water sink through sand. If you've been at the beach and you've seen the sea coming up, the sea, even though sand looks like it's solid, the sea will pass through it quite nicely. Water will pass through sand. So if you put a layer of sand in your filter and pass your water through it, that actually removes the particles that didn't get removed by sedimentation. So we've removed most of the things from water. We've got water that's relatively safe to drink, but at this point it's probably still got some tiny microscopic things that are in there, particularly bacteria that could cause us to be sick, cause a stomach illness, diarrhoea and vomiting. So the main way they do it is that they can actually pasteurise it by heating it up really, really hot, but quite often in this country our tap water gets treated with chlorine. Now chlorine is toxic. It's toxic to us in large amounts. But if you put it in a tiny amount into a water supply, it will actually kill the bacteria. Sterilisation it's called. It will kill the bacteria, and it actually is safe for our consumption. So it can then be piped to our houses and come out of our taps. They add a few other things to it, such as like fluorine for fluoride for our teeth and bones. But generally, that's the process you need to know. Sedimentation, filtration, usually through sand, and then sterilisation using chlorine. Now that's great if we've got access to like fresh water, but some countries don't have as much fresh water as we do. So they have to do what's called desalination, which means removing salt from water. There's two different ways you can do it. You can do it by distillation. Distillation is where you evaporate water, the salt does not evaporate because it has a much higher boiling point. It turns to a gas, and then you use a condenser to condense it back to a liquid, and you collect the pure water out at the end. Now they might add some things to that water to make it even better for you. Water around here, we call it hard water because it has calcium carbonate dissolved in it, which is actually good for your teeth and bones as well. So they might add a few things to that water because essentially we just have pure water after distillation. And then if you remember osmosis from biology, they do a process called reverse osmosis where they use a semi-permeable membrane and actually force salt water through the membrane, and salt gets trapped and water passes through to give you pure water at the end of it. Energy is needed for both processes. For distillation it's needed to boil the water, and for reverse osmosis it's needed to supply the pressure to push the water through. Lots of energy means it's expensive, so it's rarely used if we can get away with it. In this country we don't have to use distillation or reverse osmosis very much, but in countries such as like Spain, I believe they actually have to use it a lot more rather than us, and in places that don't get as much fresh water from rain in mountains, rivers, streams, things like that. Now we have had an hour and a half, just going to cover a couple more things just before we finish. The analysis of water is required practical. You could test the water for pH and dissolved salts. pH is easy, you just add some universal indicator. If you wanted to be a bit more scientific, you could use a pH probe. Dissolved salts, what you do is you take a sample of that water, you heat it till all the water evaporates in an evaporated dish, which you've weighed before the experiment, and then you weigh it again afterwards and find the difference in mass. Will tell you how much salt, not necessarily just sodium chloride, but all ionic salts were dissolved in the water. And in this required practical, you would probably test tap water, seawater, rainwater, and maybe distilled water. Distilled water should have no salts dissolved in it. It should have a pH of exactly 7, whereas the others, the results would vary. And in an exam, they're likely to give you a set of results, and you could try and talk about what those results mean and interpret them. We also need to treat wastewater, such as our sewage. Our wastewater is the thing that goes down the pipe, either from the toilets or from the sink. And the way they treat that, I'm not going to read all this out, but the key stages are they screen it to remove the big things that might have got into the waste pipes, which does happen occasionally. Nappies and things being flushed down the toilet, which shouldn't happen because it blocks pipes, but it does. So they remove those first by screening. Then they essentially let it settle, sedimentation again. The sludge at the bottom gets run off, and the liquid gets passed into another chamber where they treat it with microbes and let the microbes digest it aerobically, which means in the presence of oxygen. That actually breaks down the harmful things in it, and then you actually get water that's safe to then pump into the oceans or into rivers because it's been treated. They used to, years ago, just pump raw sewage into the seas, and it completely destroyed all the beaches, the wildlife within an area, because it's highly polluted. It's not nice stuff, all our waste products, and they cause a damaging effect on the environment. So now we have to treat the water to actually make it safe to put back into the water supply or the water cycle. There are two methods of extracting metals. I know I'm rushing through this, but there are two ways of extracting metals that you have to be aware of. One's phytomining, which is where you use plants, the clues in the name, P, plants, P, phytomining, which is used to extract metals from low-grade ores. That means ores that don't have much metal left in them. The plants are actually called hyperaccumulators. They absorb the metals through their roots and they store them in their leaves. You then have to burn the plants and then extract the copper, usually for a process, or sorry, the metal I should say. This is a good example for copper, but could be other metals. Usually extract the metal for a process of electrolysis or treating with scrap iron to displace it. And then bioleaching is where you use bacteria. Clues in the name, bioleaching, B, bacteria. This can be used again to extract metal from low-grade ores, but also to clean up what they call brown sites, which are areas which have probably been industrial. They've probably had industry buildings on. The ground has become quite polluted, usually with heavy metals. They can add a leachate, they can add a bacteria solution to the ground and then absorb the leachate that's produced, which is the waste materials that the bacteria, and then they still have to extract the metal out of the leachate using electrolysis or extraction with scrap iron. So, generally, last thing I'm going to cover, an LCA, new to the GCSE. It's called a life cycle assessment or a life cycle analysis. Basically, you're looking at the life cycle of a product right from where it started as the raw materials. How were those materials transported around? How was that material made, that product made? Did it have to get distributed around the country? And what happens to it after it's served its useful purpose? Is it recycled? Does it biodegrade? Is it just thrown in landfill and have a massive impact on the environment? There are some questions around here which are the sort of things you need to be thinking about when doing a life cycle analysis. I'm not going to read them all out. We need to think about where the materials come from, for example. This is a cycle because some things can be recycled back into it and be used as the raw material for another product, which is a good use of them. Okay. So, the kind of idea of this topic in sustainable development is all these bottom things. We're conserving or reducing the limited amounts of resources we've got on the planet. We're conserving the energy sources that we've got on the planet, coal, oil, gas. We're reducing waste, so we're not destroying the environment by chucking loads of waste into landfill sites. and we're thinking about the environmental impacts. Do we need to burn down so many forests for use for landfill sites, for things like that? Do we need them for the fuel, which is obviously having a harmful impact on the environment and contributed to global warming and climate change and those sort of things. Okay. So, thank you very much for watching. It's been with us tonight, if you're here live and also watching it later on. Good job watching. Finally, as I say, we'll be in tomorrow in the morning to go through things in sort of 103, talk through any last questions. If you want to go through like balancing equations such as that, I'll take you through. But I will say at this point, a lot of time spent on very little marks in the actual exam. Concentrate on the big things like we've gone through today. Try to get some added detail to the bits I've gone through tonight, and you will do amazingly well. See you later. Good night.